So a quick review of relevant year 11 information is you need to know what's called your SUVAT equations. And your SUVAT equations are basically V equals U plus AT, S equals UT plus half AT squared, B squared equals U squared plus 2AS. And what these are useful for is finding, well, each of them, you've got 3 equations, each of them has 4 variables. So if you know 3 of the 4 variables, then you can find the last one. So what are these things? Well, S is your displacement. B or U is your initial velocity. B is your final velocity. T is time. And A is acceleration. Now, when you're using these equations, remember, you must have them in SI units. So displacement is in meters. Initial and final velocity are both velocities, so they are in meters per second. Time is in seconds, and acceleration is in meters per second per second. You should also pay attention to the fact that displacement and your velocity and acceleration are vectors, which means you need to pay attention to the direction, which if you're using just one dimension, then you're looking at positive or negative. You need to take that into consideration, whether it's a positive or a negative S, U, V, or A, based on how you defined it. This will be very useful for us to use in projectile motion. And you should also remember, when can you use your SUVAT equations? You can use them when acceleration is constant. So those will play a sort of center role in what we'll use very shortly. And another thing you should remember is Newton's second law, which basically says that the net force equals the mass times the acceleration of the object. So this is the net force, is the product of the mass of the object times the acceleration of the object. And of course, you can use that to derive acceleration. Okay, do you have any questions with anything we've revised here?
For the vector part, what do you mean by like positive or negative? Does that mean like is that like kind of like which direction they go?
It is. So for example, if you've got something going to the right with 5 meters per second, then the velocity of that would be positive 5 meters per second.
Yeah, okay, yeah.
And if it's going
so
to
it's
the
like
left,
a graph kind of thing.
Well, it's simply just the fact that the velocity includes the direction. So it's either positive or negative if we keep into one dimension.
Yeah.
Make sense?
Yeah.
All right. So now, applying to projectile motion, which remember is a 2D motion. And remember your key ideas as before. It is launched at some velocity v at some angle theta. We understand it will kind of do this thing, but your key points are influenced by gravity only, which of course means no air resistance. And in that case, we've also got Galileo, which tells us that the horizontal and vertical analyses, or the horizontal and vertical components, are independent. And because they're independent, then that means they can be analyzed separately without any issue. So think about what we've just talked about. And if you consider the free body diagram, the free body diagram would then, as we discussed, mean that it's just the weight equal mg downward. So that means if we think about it horizontally, there is no net force. And if we think about it vertically, the net force is just negative mg. Of course, reminding that this is negative, and this is positive, and this is positive, and this is negative for the directions. So would you agree that those are horizontal forces is there is no horizontal component to the force, and there is only the only force acting on this object after launch is a vertical force downward with a magnitude of mg?
Yeah. Yeah.
And how do I get acceleration from net force?
What was it?
I mean, we've got net force. So how am I going to get acceleration from that?
Just divide each side by m.
Yeah, you need to divide by the mass. So as long as we've got the net force and we know the mass, if we know the mass of the projectile, if we divide it by m, we'll get a. So let's do that. Let's work out the acceleration horizontally. I mean, it's going to be the net force divided by m, but in this case, it's just 0 divided by m. So that means the horizontal acceleration is 0. Yes.
Yep.
And the vertical acceleration would be, well, negative mg divided by m, which means that will be negative g, which is approximately negative 9.8. So we have now worked out that with our assumptions, then the projectile motion will have a horizontal acceleration of 0 specifically, and a vertical acceleration of downward 9.8 meters per second. Yes.
Yep.
Is this acceleration horizontally constant? Is this constant?
Yep.
Is the acceleration vertically constant?
No.
Well, what is the acceleration equal to?
Oh, okay. Yeah, it would be constant. Never mind. Yeah.
It's negative 9.8, right?
Yeah, yeah.
Which basically means that is that a constant?
Yeah.
Now, if you have constant acceleration, what formulas can we use?
The SUVAT ones.
Exactly. So what we can now do is we can now use our SUVAT equations on the horizontal and vertical separately. So horizontally, we know that acceleration horizontally, which often in physics we'll do as ax, that's 0. The acceleration vertically, which we'll often deem by ay, is negative g. Okay. So with that in mind, we now need to figure out what the velocity is and what the displacement is. And that's what we want to do. Now, our SUVAT equations are v equals u plus at in general, and s equals ut plus half at squared. Those are the two we're going to mainly use today, although we can use the third one as well. So just keeping that in mind in the lower right-hand corner. So if v equals u plus at, then we can work out v horizontal, and I'll use x here, equals ux plus at. But what's our ax?
0.
So that means our vx equals ux. Does that make sense?
Yeah.
So what is that? What does that mean in other words? If vx equals ux, what are we saying about a horizontal velocity?
It's the same throughout. So like,
So the word to describe that is that it is constant.
yeah.
We're going to have a constant horizontal velocity throughout the motion as a result of the fact that acceleration is 0, which means there is no acceleration. All right. And of course, Sx will equal ut plus half at squared. And ax again is 0. We know that, which means they will still just simplify down to ux times t. So we now have expressions for the horizontal acceleration, velocity, and displacement in terms of the initial horizontal velocity and time.
Yeah.
And we should consider what happens at the start because we want initial velocity. So the initial velocity is the launch velocity v at angle theta. And would you agree that you can separate this into horizontal and vertical components?
Yep.
And these are at right angles to each other. So this would just be ux, and this would just be uy. So what is ux equal to while we're on this?
Vx.
Well, how do we find this component? You've got a right angle triangle. You know the hypotenuse. You have a representation of the angle. How do we get this horizontal component?
Oh, I do. Cos theta.
So if you look at cosine theta, that's going to be adjacent, which is your ux, over v. And if you move the v over to the other side, that will then mean that ux will equal v cos theta. We will do something similar with uy. What trig ratio might we use for uy?
Sine theta.
Yeah, because sine is opposite over hypotenuse. So if you use sine, we'll have opposite, which is uy, over the hypotenuse, which is v. And so we'll have uy over v, which then means your uy equals v sine theta. So in other words, it is ux, vx is just ux, and sx is ux times t. And then, of course, you need to work out what the initial velocity is. The way you work it out is always the same, but you can choose not to remember this if you feel it's easier to sort of work it out as you go. But ux would equal v cos theta. And so that means a different way to write these expressions would, in terms of v and theta, would be this is v cos x, and this is vt cos theta. Okay? This is v cos theta, and this is vt cos theta. Now, let's now apply it to the vertical. This time, the vertical has an acceleration of negative g. And the two things I've boxed in red, you can always assume in physics. Without any problem, you can always, based on your theory, say that there is no horizontal acceleration in projectile motion, and that the vertical acceleration is always downward with a magnitude of g, which is 9.8, or sometimes often they round it to 10. You'll just be guided by the question as to what number they want you to use for g.
Yeah.
I'm just going to keep it as g here, because sometimes you use 9.8, sometimes you use 10. Okay. So we're going to just now apply it to the vertical velocity. So vy equals uy plus ayt. Of course, we know uy already. Uy is v sine theta. If you're not comfortable with using v sine theta, then just stick with uy and work out what uy is using a diagram. Yeah. Ay is negative g, so that's just going to make negative gt. And that would then give you what the velocity in the vertical direction is at each point.
Yep.
Sy would equal, assuming you start from the origin, uyt minus a half ayt squared and then that's really just SUVAT, but using them in the vertical direction. If we sub in what we already know, then that's of course going to be vt sine theta minus g over 2 t squared. Okay. So it's important for you to recognize what we've got here. We've got a horizontal acceleration is none, vertical, and that means the constant velocity horizontally. Whereas in the vertical direction, we have a constant acceleration downward. And that means that your velocity is changing. So this is linear, as is this. And that this would then be, well, a quadratic. However, while I did say that the key things that I often tested in multiple choice and so forth is the ones I'm circling or emphasizing in yellow. So as an emphasis, you understand the horizontal acceleration is 0, which is none. The horizontal velocity is constant and not 0, unless you're just dropping it. And the vertical acceleration is constant, and the other things are not constant. Okay.
Yep.
So those are your key equations. Just quickly write them out on the next page. And you do need to know these. These are on your formula sheet, but you should know them very well because they, well, form the basis of your understanding of projectile motion. Okay. So the next thing we'll look at is how we might talk about these graphically with some ST-UT-VT graphs, AT graphs that we did from earlier in the year, but a little bit of revision sort of may help there.